Okay, this is the first example, which is two-dimensional example. We're going to use this one two links mechanism to explain the basic setup of the DH convention method. So this, since we know this is a two-dimensional configuration, we attach x naught and y naught at the first joint, and we attach x1 and y1 at the end of the first link, and we attach x2 and y2 uh, at the third joint over here. So the z-axis are all perpendicular to x0, y0, x1, y1, and x2, y2 plane. And obviously, they are all parallel to each other, which means the twist angle between z0, z1, between z1 and z2, they are all zeros. That's given. And again, since this one is two-dimensional configuration, the distance between the joints about on z-axis, they are all zeros. So those two things are given. So in this case, we only need to worry about two other parameters. The first one is the theta, which is rotating about z-axis. So we got two theta over here, theta 1 and theta 2. And we also got two offset along the x-axis. One is this one, and the other one is this one. So we're going to define those kind of stuff. So first thing we need to do is to build a table. I got two links. I got four coefficients. Keep in mind, those two are x direction. Those two are z direction. And since this is two-dimensional plane and they have no thickness, so d is going to be 0. Again, all the coefficients, all the z-axes are going to be in parallel. So the twist angle are also zeros. Now, there are two things we wanna do. Theta I and theta the theta I over here, but those two are going to be changed over the time when you start to move. So we can just do theta 1 and theta 2 over here. And those two can be just variables. But the linkage A1 and A2, they are kind of fixed number, so you can attach any number you want to. But at this moment, we just put A1 and A2 over here. Then we can start to do all the calculation over here. Based on what we have in the previous pages, we are having the transformation matrix in four directions, but we do not have any D and we do not have any alpha, which means this one and this one, they are going to be identity or I matrices over here. So the important thing is if we can come up with the joint angle matrix and the link length matrix, then we'll be fine. But what are we going to deal with that? So that's from zeros joint to the first joint. If we do that, keep in mind, this is two parts. Well, maybe I should not use this one. Let's move back a little bit. Then, oops, we deal with that. Okay, that's fine. So the first one is going to be rotation, and it is going to be about the axis. So it's going to be cosine theta 1, sine theta 1, negative sine theta 1, cosine theta 1, and 0, 0, 1, 0, 0. That's my rotation matrix. And nothing fancy. This is going to be my rotation matrix. Theta about z. For the second one over here, we are having 1, 1, 1, all the others are zeros. Okay, this part over here, what are we going to do? Because everything must projected to x0 and y0. So we know this is a1, so when we project everything over here, it's going to be a1 cosine theta 1, and this part over here is going to be a1 sine theta 1. So if we put everything back to this matrix, it's going to be a1 cosine theta 1. This is going to be a1 sine theta 1. CS is of course 0. The other two matrices we don't really care because they are identity. So it doesn't matter where you put it in the sequence. It is going to be omitted anyway. So if you come up with an equation like this, you're going to find this specific configuration is going to be C theta 1 sine theta 1 negative sine theta 1 cosine theta 1 0 0 0 0 1, and this is going to be a1 cosine theta 1 a1 sine theta 1 0. Sorry, this is 1 0 0 0. So this is going to be my first transformation matrix. Now if we want to do the second from join 1 to join 2, keep in mind we are not related to x0 and y0. Instead, this is going to be your original matrix from now on, which means we can do the same configuration, but this time the offset is going to be a2 cosine theta 2 along this direction, and it's going to be a2 sine theta 2 along y direction. So if we do something like that, h1 to 2 is still rotation z1 theta. So it's going to be cosine theta 2 sine theta 2 negative sine theta 2 cosine theta 2 0 0 0 0 1. That's my rotation. And just standardize everything. That is going to be my rotation. The second one we need to do is translation x1 with a. So this one over here is going to be the same 1 0 0 0 1 0 0 0 1. Everything remains the same. But those two components over here, they are a2 cosine theta 2, a2 sine theta 2, and 0. This one is going to be my second transformation matrix. So if we combine those two together, that is going to be something like this. Sine theta 2, a2 sine theta 2, 0, 0, 0, 0, 1. So we got our transformation matrix between 0 and 1 and between 1 and 2. So the transformation matrix is going to be this one. If you combine all those things together, you're going to multiply this matrix with the matrix we defined earlier. So it is going to be a long 1 cosine theta 1 minus sine theta 1 sine theta 1 cosine theta 1 0 0 0 0 1 0 0 0 a1 cosine theta 1 a1 sine theta 1 0 and 1. The second matrix over here is going to be cosine theta 2 sine theta 2, negative sine theta 2, cosine theta 2, 0, 0, 1, 0, 0. Bottom over here, they are all zeros. And this is A2, cosine theta 2, A2, sine theta 2, 0, 1. Combine everything all together. We got a big matrix. Cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2. This one over here is going to be sine theta 1, cosine theta 2, plus sine theta 2, cosine theta 1, 0, 0. Over here is going to be negative cosine theta 1, sine theta 1, minus cosine theta 2, sine theta 2. Am I doing right? And this one is going to be negative sine theta 1, sine theta 2, plus cosine theta 1, cosine theta 2, and we have 0, 0, 1, 0, 0, 0. And over here, I got A2, cosine theta 1, cosine theta 2, minus A2, sine theta 1, sine theta 2, plus A1, cosine theta 1. Second component over here is going to be A2, cosine theta 2, sine theta 1, plus A2, sine theta 2, cosine theta 1, plus A1, sine theta 1. The other two components are 0 and 1. So if we can come up with the transformation matrix, just multiply them together, we got a big matrix. Normally, the calculation over here is a little bit tedious. So I would suggest you guys use MATLAB or other math tools to check whether your answer is correct or not. Okay, that's my first example. The second example over here, the first example is two-dimensional one. This one is going to be a three-dimensional one. So again, before we start, we will need to identify what are my x, y, z directions for individual parts. And after that, we're going to use a table to simplify our calculation. So I got one linkage over here, second linkage over here, and third linkage over here. So individual ones, we would need to define what are the four parameters for individual joints or individual link. So since we have three links, so it's going to be 1, 2, and 3. What do we need to define? AI, alpha I. We also need to define DI and theta I. Okay, let's start from this one. This one is going to rotate at about z-axis, so it's going to be z1, theta 1 over here, and join 1, join 0, and join 1. Actually, got the distance over here, and the distance is d1. So I put d1 over here, but since this movement, the configuration is along z-axis only, so there is no distance or no offset along x direction between join 0 and join 1. So this one over here is going to be 0. And z1 and z0 is actually on the same axis, which means there is no twist over here. So this is something we're going to have. Now, that is my first coordinate, my first link. The second link, I got x, y, z over here, and I got x2, y2, z2 over here. So let's start configure what's going on. This one over here is a joint that is going to move vertically, which means this one cannot be rotated. If this one cannot be rotated, certainly the theta is going to be 0. Okay, and again, the distance, the third joint is above the second joint, and this one is going to move up and down with the distance d2. So we got d2 over here, but since they are along the z1 axis, the x1 has no movement, which means my a2 is going to be 0. Nothing fancy. This time, be careful because my z1 is this direction, my z2 is this direction. So the angle between those two are going to be minus 90 degree. So since they are not along the same line, we must identify what is the angle between those two z-axes. That is something we need to do. And when you look at this one between this joint and the end over the third joint over here, this one is going to move in this direction. So the d3 over here is actually moving along z2 direction, which means I must define d3 over here. This time, my x direction is over here. My x3 direction is over here. So we are aligning x2 together with x3. So it's not moving. There is nothing moving along this direction or x direction in the second coordinate or third coordinate, which means my a3 is 0 in this direction. Some of you guys might think, okay, I define my y over here, so when you start to move, this one must have some a. Is not the case, because when you are defining your d and a, it must be following the local coordinate system. Do not mix this up together with other coordinate. It's going to be a wrong calculation if you are just doing something like that. Okay. Now, there are a few things we need to define alpha and theta. Clearly, this one is translation only. There is no rotation component over here. So theta 3 is going to be 0 as well. And z2 is going to align correctly with z3. So the twist angle is 0 as well. So this completes our table used for calculation. So we can start to generate everything individually. So let's start from h0, 1. This matrix and this matrix, the A matrix and alpha matrix, one is rotation, the other one is translation. Those two are going to be identity. So what we actually have is going to be rotational matrix Z not theta 1, Z not theta 1, and translation Z not D1 multiplied by I and I. Those two i's are corresponding to A and alpha. So if we do that, we will have the rotational, which is going to be cosine theta 1, sine theta 1, negative sine theta 1, cosine theta 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. The translation is going to be along z direction. So it is going to be d1 over here. Pretty straightforward. Then if we do everything, you're going to find this is going to be c theta 1, sine theta 1, negative sine theta 1, cosine theta 1, 0, 0, 0, 0, 0, 0, 1, 0, and this is going to be 0, 0, d1 and 1. I'm sorry, this one should be 1. So this is going to be my transformation matrix from 0 to 1. Pretty straightforward. The second one over here, 1 to 2. We're going to do the same thing, but this time this is going the matrix corresponding to those two, they are going to be identity. So the only thing we need to worry about is the rotational of the twist and the translation of the distance. So when we are doing something like that, we can actually combine everything all together, but let's not do that. We are having our 1 0 0 0 1 0 0 0 1 0 0 0 0 0 D2 and 1. This is corresponding to the translation. Keep in mind I'm following the same uh, uh, sequence defined by the formula. Then the second one over here, let's use this one as 0 0 1 0 0 0. So this time the alpha is going to be negative 90 degree. We got it's along x direction, so it must be something like this. So if you go back to the slide we have in module 2, we can actually identify those parts with cosine and sine alpha in this for those four components. If you follow that, you're going to find out, or you can just use the projection over here. So x2 is going to be the same as x1. Z2 is going to be along y1, so it's going to be 1 over here. The z projected to the OY, but the y is projected to the negative OZ. So it's going to be negative 1 over here and 0 over here. So this complete my transformation matrix. Then we just put everything all together. You're going to find this is how we find the second transformation matrix. Now, if we want to do that, H2 to 3. This time is going to be straightforward as well because I got three identities. The rotational about z-axis, which is corresponding to theta, and the twist angle, which is corresponding to x alpha, and the one with a. So I got a single matrix, which is going to give me, where is it? 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, D3, and 0. So I got my H01, H12, and H21. So my transformation matrix is going to be combine everything all together. And that is going to be my transformation matrix. Let's take a break here. So we're going to use another video to explain the third example.